radical properties and simplifying radical expressions. We'll first go over the radical properties that will help us simplify the radical expressions we'll come across, and then we'll bring up some strategies that we can use in an attempt to simplify some expressions. So let's start with, I have the nth root of some expression A times the nth root of some expression B. We can combine those into one radical as long as the index of each radical is the same by multiplying the expressions that are underneath in each individual radical. So I could express it as the nth root of A times B. Now, working in both directions of this property could be a useful tool. So not only when we see radicals of the same index being multiplied can we combine them into one, but if we have a radical where there are multiple terms underneath it being multiplied, you could split them apart, and that could help you in your simplification process as well. So learning to work in both directions is a useful skill set. Now, we also have the nth root of A over the nth root of B. Again, as long as those radicals are of the same index, n, we can combine them into one radical of nth root n of the quotient of A and B. And again, working in both directions is a useful tool. So if I see the nth root of A over B, I could split that into two separate radicals, one taking the nth root of A in the numerator and the nth root of B in the denominator. And the last property we'll talk about is, let's say I have some expression A raised to the power of m over n. So this is a rational exponent. So we have this ratio of two values. And in the event we have a rational exponent, we know a radical is present. And the index of the radical that is present when we see a rational exponent is equivalent to the denominator of that rational value. So when I say A to the m over n, that means I am working with an nth root. So if you saw denominator 2, you have a square root. Denominator 3, cube root. Denominator 4, fourth root, and so on and so forth. That numerator m tells you what the power of the expression underneath needs to be raised to, or you could format it as the nth root of A all to the power of m. So both of these work, and the reason why is because A to the m over n can be restructured as A to the m times 1 over n, or A to the 1 over n times m. Because the order of the multiplication of real numbers does not matter, I could first raise A to the power of m, then take the nth root of that, or take the nth root and then raise it to the power of m. That's why either of those are sufficient. Now, is there one that's better than another? Well, oftentimes, if A is of a large value, taking the nth root first will reduce the size of that number, and then raising it to the power of m may be an easier computation in the event that you don't have a calculator available. So this second formatting, doing the nth root first and then raising it to a certain power, is oftentimes easier if we don't have a calculator or computer to handle that computation for us. So those are the properties we want to be aware of. And other properties that we should be aware of that I'm not going to include or write down right now is just basic exponent properties. So when do you add exponents? When do you subtract them? When do you multiply them? What happens if you have a negative exponent? So things like that can pop up. But having said all that, let's talk about some strategy for simplification. So we're going to talk about, let's say we have a radical of just some number. So let's say we have the cube root of 500. So we have a radical expression here, and we want to simplify this as much as possible. So we talked about square roots of numbers at the beginning of the year, how we simplify those. We might first want to determine, well, is 500 a perfect cube? And the way we can do that is if we just take a calculator and do the cube root of 500. If we get some crazy decimal, it's not a perfect cube. If we get a nice clean number, then we can call it a day and say the cube root is that value. But if we don't have a calculator available, we can break down that 500 into a prime factorization. So it's divisible by 2 because it's even. 250 can be broken down. 125 can be broken down. And 25 can be broken down. So when I break down those numbers, I'm just going to cross them out so I don't confuse them for values that I am still considering. But we have this prime factorization of 2 times 2 times 5 times 5 times 5. And we're trying to figure out how can we simplify the cube root of that, right? So 500 can be expressed as the product of 2 times 2 times 5 times 5 times 5. Now, what we said with square roots at the beginning of the year with our quadratics unit is that we want to find groups of 2 because groups of 2 imply that that value could be expressed as that thing squared. So when we're looking at cube roots, we want groups of 3. And the reason we want groups of 3, like this group of 5 here, is because we could say 2 squared times 5 cubed. We're trying to find the cube root of that. And from those properties we just introduced, here we have a product of 2 things underneath a radical, so I could split this if I wanted to. And the cube root of 5 to the third is just 5. Cube roots of 4. And there is your simplification. And going back to the strategy that we employed with the square roots at the beginning of the year, how does this connect? We have our group of 5. For every grouping we make, we remove that value once per group. Anything that did not get grouped in the prime factorization must go back underneath the radical. There are 2 2's, so we multiply them together, and we still get the same result as what you showed below. But I show that breakdown below. That way we can see the utilization of those radical properties that were brought up at the beginning of the video. So that's how you handle the simplification of a radical of a number. And again, the grouping size is dictated by the index of the radical. So square roots, groups of 2, cube roots, groups of 3, fourth root, groups of 4. And number of groups tells you the number of times to remove that number outside of the radical. If you have to put multiple numbers back in or multiple numbers are removed, make sure you multiply them together. So there we have the simplification of just a constant value under a radical. But what if we have to simplify a variable under the radical? Well, you could use the same strategy. So you could break down x to the 11. All that's telling you is you have 11 x's. And you could say, I need groups of 4 because we have fourth roots. So there's a group of 4 x's, there's a group of 4 x's. So I pull that thing out once per grouping. So I pull out one x for the first group, I pull out another x for the second group. Anything that did not get grouped needs to go back underneath. There's 3 of them. So we can say our final answer should be x squared, fourth root of x cubed. That's a simplification. So you can still employ that strategy where you break down the value that's underneath the radical and then use grouping method, group size indicated by the index, and carry that out. But there are some scenarios where, so we had to write down 11 x's. Like what if this was like a really large number, like 35? I wouldn't want to write out 35 x's. So is there a better way to approach this? So actually, let's work with 35. So the fourth root is the same thing as a exponent power of 1/4. And with multiplication, so exponent properties, we know we're supposed to multiply these, so I'm going to get 35 over 4. So here's the trick we can do. We can change this to a mixed number exponent. So 4 goes into 35 8 times, with how many left over? 3/4. So this is the mixed number equivalent. Then we could split this back up again. And we could say that we have x to the 8th plus 3/4. By the way, it's kind of a long way, and I'll show you there's the shortcut at the end. But I just want to show you why this works, the strategy that I'm going to show you at the very end. So 8 and 3/4 is the same thing as 8 plus 3/4. In exponent properties, if we know when we see exponents being added, we could move them back into the following: x to the 8th, x to the 3/4. To the 3/4 means the same thing as the 4th root of x to the 3rd, and there is our simplification. So what we did was we reformatted the radical as a rational exponent. We know our exponent properties, so we multiplied them together. I reformatted it as a mixed number. That mixed number can be expressed as a sum. Exponent properties tells me when I have a sum of exponents, I can split it into two separate terms. Then I take the term with the rational exponent and reformat it back into a radical expression, and there's your simplification. Now that seems like a pretty long process to do. Is there an easier pathway? And the answer is yes. So here's what you're asking yourself. When you have a variable term underneath the radical that you want to simplify, you're going to ask yourself, how many times does the index go into the exponent? Now, 4 goes into 35 8 times. So that tells you how many x's or how many of that variable needs to be removed out of the radical. So I need to take out 8 x's. Now, it goes in 8 times, but how many is left over? Well, there's still 3 left over, and that's the amount that needs to go back underneath, and we get to the same place as we did before without going through that long process. So we'll look at one more example. Let's say I have the cube root of y to the 17. I'm going to say, how many times does 3 go into 17? It goes in 5 times, so that's how many y's I should remove. How much is left over? Well, there's 2 left over, a remainder of 2. So that's how many y's need to go back underneath. And also splitting the cube root of 17 into the largest perfect cube, we could say y to the 17th is the same thing as y to the 15th times y squared if we know our exponent properties. And then using our radical properties that we introduced at the beginning of the video, I could split that into the following. The cube root of y to the 15th is y to the 5th, cube root of y squared, and we get to the same place. So a bunch of different strategies you can use. The one I prefer is, how many times does the index go into the exponent? That's how many I take out. What's the remainder? That's how many go back underneath. And lastly, what we might see is a combination of numbers and letters. So what if we had something like this? Well, you see there are 4 terms underneath this radical. So you can think of this as like 4 subproblems where I can do the cube root of 252. I could do the cube root of x. I could do the cube root of y to the 7th. And I could do the cube root of z to the 3rd and handle each one on its own and then multiply the result at the end. So that's another strategy you can utilize. So there are some properties, some manipulations. It really takes some exposure to various problems and practice with using these different properties and strategies to get to the end result. But I'll leave the video at that point. And actually, instead of ending the video there, I do want to bring up one more thing, is like, what happens if you have 2 radicals that are trying to be combined but are of different index value? So we have square root and a cube root. Can we put these together? Well, as they're currently formatted, the answer is no. And that's where the transition over to a rational exponent is useful. So if we rewrite this as x to the 1/2 and x to the 1/3, knowing that the denominator of the rational exponent indicates the index and the numerator is the power of that expression underneath, or what the entire radical is being raised to. So in this case, it would be the power of 1. What I can do is, because x and x, these are of the same base value, I am allowed to combine these, or even if they weren't of the same base value, let's change this to a y just for the problem. If I wanted to figure out how to combine these, well, I can get common denominators for these fractions, and that would tell you what the radical should be in the event I want to combine that. So if we say, I'm going to rewrite this as to the 3/6 and y to the 2/6, well, then I can go back and say this is the 6th root of x to the 3rd and the 6th root of y squared. And now, because they are the same radical, I can combine them into 1 and say x to the 3rd y squared. So combining these two, if the goal is to put them underneath one radical, I was able to do that by putting them under a 6th root. So I had to change the whole radical, but that's not a difficult task if I'm aware that there's a reformatting into a rational exponent form that I can leverage, change into common denominators for each, knowing that the denominator represents the index of the radical. So just a neat little strategy if you're attempting to combine radicals that are of a different index. So we were able to take square root, cube root, and combine it into one 6th root. And that is where I will end the video. So various strategies that you can employ when trying to simplify radical expressions, and 3 major radical properties you should be aware of.